Hello everyone and welcome to today's webinar. My name is Sam Webster. I'm a Senior Technical Trainer here at SMT, and today we're going to be talking about splines in MASTA. The webinar today will be no longer than 1 hour in duration, and if you do want a copy of the presentation as I'm going to show it now, then you should be able to download it from the GoToWebinar window. There should be a section called Handouts where you should be able to get a PDF version of this presentation. The recording of this webinar will also be available on our Wistia account quite soon after the completion of the webinar, and I'll email all of the attendees after the webinar as well, just to make sure that you've got access to that material. So what we're going to be going through today is just a general overview of how splines in MASTA can be modelled, the different options we have available when modelling splines, and the longest part of the presentation today will be actually going through how to model a flexible spline. So this is where we use an FE model in place of the spline, and is the most realistic method we have of modelling a spline within MASTA. So that will take up the most time. If you have any questions as we're going through, please do ask away. There should be a questions panel on your GoToWebinar screen. I can't promise that I'll get to them during the course of the webinar, but I'll either answer them at the end of the session, either in voice or in text format. So what I want to start off with is the concept spline within MASTA. This is something that many of you will be familiar with. So if I just hop over to MASTA itself. So this is the model I'm going to be using for a lot of the session today. It's one of our tutorial models. It's a transfer case in this case. And we'll be focusing on this particular spline here, which is a splined ring gear into a housing. Now, the spline component is not something on its own. It actually comes in as something we call a shaft hub connection. And this can be a few different types of component. So it can be a rigid bond. It can be a concept spline. It can be a detailed spline, which we'll cover as well. And it can be a detailed interference fit. Now, if you want to actually model a spline, you add in one of these shaft hub connections. That will initially come in as a rigid bond, which will be a purple component. And you can change its type by choosing this type property on the properties window when you have that component selected. So we will start off with a concept spline. A lot of the properties, or pretty much all of the properties for your spline, can be accessed down in the bottom left properties window. However, there are reports that have been created to make this data input much more workable. So if you go to the editor with your spline selected, then we'll get a series of reports which allow us to input the appropriate information. So as we mentioned, I'm going to start off with a concept spline, moving on to a detailed spline in a little while. And the first thing I want to talk about is the different stiffness types that we have available. Now, this is various ways in which we can specify or calculate the stiffness of the spline connection. I'm going to do this with the aid of that PowerPoint presentation. So, starting off with the simple stiffness specification. So this is the one we have by default when we choose a spline. And a lot of the properties, although I said they might be available on the editor, a lot of the properties that coincide with this are available in that properties window. So for example, we have the ability to specify preload and stiffness values. So with a simple stiffness specification, we've got manual specification of axial, radial and torsional stiffness, which you can see on this image of the properties grid here. By default, they will be very stiff at 1E12, but they can be modified. Tilt stiffness can either be calculated, which you can see there is done either with length and radial stiffness, or it can be directly specified. So you can change this to say you want to actually specify the tilt stiffness as well. You do also have basic specification of clearances. So you can see we've got radial clearance there, and if you specify a radial clearance, it will be able to calculate the tilt clearance for you. And we've got basic specification of preloading as well. With a simple spline, there is no specification of spline tooth geometry. This is literally all we're specifying at the moment. You will notice as well that there is an additional specification of the coefficient of friction. And this is to calculate the maximum axial load before you experience slipping. And this gets fed into a report table that we'll find when we look at the reports a little bit later on for the results. So looking at some of the available results for a simple stiffness spline. So we'll start off with the actual node model that we see. So when we're looking at a simple stiffness, the spline is reduced to the stiffness between two central sets of nodes along the spline length. So as you can see here, we have a set of nodes for the inner connection, a set of nodes for the outer connection, and then our specified spline stiffnesses control the stiffness between those two sets of nodes. In terms of report outputs, we've got the forces and the displacements on each of those nodes. So we'll be looking at the actual reports in a second within MASTA itself, and this is the format we'll see. So we'll see node forces and node deflections in local and world coordinate systems. And just to reiterate, with a simple concept spline, there are no spline ratings included. Okay, so next we have the ability to specify a matrix specification. So this is the specification of spline stiffness in 6 degrees of freedom. You can see a little pop-up over on the right-hand side image there. So basically, instead of manually specifying the stiffnesses within our property grid, we open up this separate little window as well using this icon, where we have a 6x6 grid of the node. In this case, there's only one central node instead of 6, and then we can specify the stiffness. So with this type of specification, there's no specification of clearance or preload. The stiffness is just being handled by this input here. So the results when we're specifying a matrix. So the spline is reduced to the stiffness between two central nodes. So instead of having a complete line of nodes here, we've just got a single central node. And it is the stiffness between the inner and the outer connecting node. And then when we're looking at the results, we see the node forces and displacements calculated and then displayed in our reports. So when we're looking at the actual assembly, so the image on the right here is just of the node model of the spline, and then on the left we have the actual node model of the shaft assembly, including that spline. Now what you can see is that there's multiple nodes along the length of the spline there, not just one. So the behavior of this one node is extrapolated to the shaft nodes covering the complete spline length. And yet again, as with the simple stiffness specification, there are no spline ratings using this method. Next, we have a non-linear stiffness specification. So this is the specification of spline stiffness against position in 6 degrees of freedom. Again, we have no specification of clearances or preload. However, this functionality is not normally utilized for a general spline model. So although it is available when you have a concept spline specified or a detailed spline, you will usually find people using this for mount stiffnesses. So usually using a rigid bond, for example, rather than a spline. But the option is there if you feel it can be useful. And then again, the results and the node model are very similar to the matrix method. Okay, and then the last option we have on that drop-down list is an individual contacts specification. Now, this allows us to specify a limited set of tooth geometry. So we can have tooth quantity and locations. We can put on a level of crowning and relief on the tooth flanks. We can input a helix angle and a pressure angle. It's important to note that the geometry specification that we can see there is for stiffness calculation only. It is not for ratings. We're still not doing any ratings at this stage, at this level of specification. At this stage, we are still using a concept spline. We do have the option as well to choose between a side fit and a major diameter fit. That basically chooses whether we are radially constraining our teeth as well. So within the specification here, we can put in a nominal clearance and we can calculate or specify the contact diameter. We also have the ability to specify the contact stiffness. There will be a default value that's put in the settings. However, this is just a generic default value, so you're probably going to want to modify this based on your system. So I mentioned that we can specify the helix angle, which is further down here in the settings. But you need to be aware that the helix angle specification is only with a concept spline, not with a detailed spline, as we'll be coming on to, because the geometry standards don't allow us to input that kind of information for a detailed spline. Looking over on the right-hand side here, we have some of our input properties for an individual contact spline. So what you'll notice is that there's a section for each of our specified gear teeth. So we specify the number of contacts per direction. This is basically how many gear teeth, spline teeth, sorry, that we have. And then it's giving us some corresponding information on those particular spline teeth, including the ability to input pitch errors on there as well, if we want to add some additional information. We have got the option to choose between equally spaced teeth, as we will have in most cases, or we can use unequally spaced teeth, which is useful for face splines. And this is the kind of results format that we will see. So remember, at this stage we are still using a concept spline and there is no FE or anything included in the model at this stage. This is still using that simple component. So the kind of results we can get, we can see the forces and the surface penetrations calculated at each of the tooth locations. So for example here we've specified that there's 8 teeth on this particular example spline. So we can see that there's individual force lines being calculated, force arrows being displayed on each of those concept teeth. And then if we look a little bit further over to the right hand side, you can see we get the contacts for those individual specifications. So we have the left flank contacts, we have the tooth center contact if we specified a major diameter fit, and we have the right flank contacts. As with a couple of the other methods we've looked at, the behavior is translated onto one central FE node, which is then connected to the shaft or the housing. But then when we're actually extrapolating, or when we're actually getting that in more detail, that behavior from the one node is extrapolated to all of the shaft nodes, covering the complete spline length. And then with all those inputs and the calculations that have been performed, the spline stiffness matrix is generated based on our geometric inputs. But again, this is still just a concept spline at this stage, so there is no spline rating performed. So moving now on to detailed splines. And this is surprisingly not that much extra difficulty from a concept spline. So first off, I want to start with a comparison with the concept spline component, because maybe it doesn't differ quite as much as many users think. So what a detailed spline specification in MASTA, and just to reiterate where that is, instead of specifying a concept spline or a rigid bond, we have the ability to specify a detailed spline here. So this allows users to input the designed spline tooth geometry. And then on top of that, we can use identical stiffness types between the two specifications. So as with a concept spline, on a detailed spline, you can do a simple stiffness specification, you can do a matrix, or an individual contact. The node results per spline type are identical between the concept and the detailed spline. The main difference is that inputting the detailed spline geometry, so we're actually inputting the tooth geometry, that allows some of the stiffness values from that spline to be derived rather than be directly input. So the stiffness values that we can derive from having that geometry, we will get MASTA to calculate rather than having to specify. And we've also got the ability to do some rating results of the splines as well. So things such as safety factors, we can only calculate those using a detailed spline specification. So a very brief overview of specification rating or specification standards and rating standards for splines. So we can specify detailed spline tooth geometry to obtain spline ratings in line with various standards. So the specification of spline type, we've got a list there of the different types of specification that we can perform. And then in terms of the spline rating type, there's only certain ones that can be utilized for different input specification types. So we've generated a little table here which will show you what rating types you can use for each spline type. So it's worth mentioning that we do have the ability to do a custom spline as well, where we can manually input a lot of the information that's automatically generated based on these standards. Okay, so the spline half inputs, so we'll find that with most of the rating or specification methods that we can specify, we'll have a couple of spline half tables. These can be accessed in the same kind of place. So if I change my spline type to be a detailed spline, again, just in the editor with the spline selected, I get my spline half tables, which may change dependent on the type of spline we have specified. Additional joint information might be available, such as tolerances, and we'll have an image of the spline at the bottom as well. So certain stiffness, clearance, and preload information remains manually specified in a detailed spline. So stuff that we can't calculate from the spline geometry. So this, for example, I've set this to be a detailed spline, of course, so I've got some input information here. But if I go down to my properties window in the bottom left, you'll see that we still do have some stiffnesses specified in the same way. Okay, then just a little bit of information on the available rating results. So again, the available specific results available might differ. The format might differ based on your selected rating standard, but this is the kind of thing you can expect. So looking at the actual model itself, you may actually see a representation of the spline teeth, which you can probably see there. And then you'll see individual force arrows from each of those spline teeth if you are using individual contacts, which is the most realistic method. What we're more interested in is the report, which will show us a summary of safety factors for the spline based on your selected load case or duty cycle. And then obviously again differing based on your selected standard, you'll get an output report as well showing you your ratings table for the spline joint. Okay, so next I want to talk for a couple of minutes about spline fit systems. Now this may seem a lot more detailed than the rest of the topics covered in this sort of general spline overview, but it's something that's been requested quite a bit or queried quite a bit in our support tickets. So I'm gonna cover it here just very briefly. So what I'm looking at here is the ability to specify various properties to do with the actual and effective spline fits. And this is hopefully just going to clarify what those are. So just as a bit of an overview, obviously internal and external spline halves are designed to have an equal fit clearance over all the spline teeth. In reality, the fit clearance varies on a tooth-by-tooth basis, which can impact the spline assembly and the resulting operational performance. So the manufacturing process will always ensure that form and size deviation occurs, which prevent a perfect fit. Right, so actual and effective fit systems. So this is where the confusion sometimes comes in. So starting off looking at the definition of the actual measurements. So the actual is the circular dimension of one tooth or space width as it actually exists independent of the other teeth. Now this is represented somewhat by this red image down at the bottom here. So the actual tooth thickness is, as you would expect, at the PCD, it is the thickness of the tooth as it actually exists. And then the actual space width is the same again, so at the PCD, the measurement of the actual existing space. So this is the manufacturing tolerance, which we are calling the actual, and it's needed for the adjustment and wear of tooling in order to calculate that information. And this gives us the max and minimum actual tolerances that we're going to use in a little while. And it's important to note as well that the actual dimensions determine the strength of the tooth. So this is one of the main things we need this dimension. However, if we look over at the effective, which is represented by blue, so this is equal to the corresponding tooth thickness or space width at the PCD of an imaginary perfect mating spline. So what I mean by this, again, just using the simple image, so the external effective tooth thickness is the actual, or what's referenced on the actual measurements is the actual space width. So this is our effective tooth thickness. And then our internal effective space width is actually what we're measuring as the actual tooth thickness. So with that in mind, just reading that again, equal to the corresponding tooth thickness or space width from the actual at the PCD of an imaginary perfect mating spline. So if there was no clearances, for example, no spaces, they just fit perfectly together. So the effective measurements, they include the actual measurements and the variations from ideal due to manufacturing deviations. So the form tolerances that we're looking at, or what we're calling the effective, can only be determined by metal to metal fitting of that ideal mating gear. So again, just reiterating what we were saying up here. So if we're looking at this, just metal to metal fitting, no clearances whatsoever. Okay, so the effective dimension controls the clearance of the spline with its mate, and the effective tooth thickness, or the space width, is dependent on the relationship of the tooth to the other spline teeth as well. So they're not just independent. So what we've got here is just a little diagram to show how we're utilizing those measurements, or what they're actually referring to. So the ones on the left are the same as what we've already seen, so the actual and the effective measurements. And then what we're looking at in the middle is just a spline loaded, essentially, so with the clearance taken up on one side, and then we've got the actual clearance, or the total clearance over on the right hand side of the spline. And then the two images that we can see, the two diagrams on the right hand side, are looking at the tooth thickness, so the section here, and the space width, so the section here. The red lines indicate tolerances of the actual measurements for each of those, and the blue lines represent the tolerances of the effective measurements. So what we have there is the minimum and the maximum actual, and then the minimum and the maximum effective of the tooth thickness side, and then the equivalent over on the space width side. Okay, another couple of bits of information added to our simple diagram here. The purple line here, as you can see them, are going between the maximum and the minimum, either of the actual or the effective. And these are the machining variation. So these define the tolerance of the actual tooth thickness, but that's also reflected in the tolerance of the effective tooth thickness. So they are the same measurement. Okay, and then with the green, as you can see represented in a few places, this is the variation allowance. So this defines the difference between the minimum and the maximum. Pardon me, that defines the difference between the minimum actual and the minimum effective, or the maximum actual and the maximum effective, and so on. And this is considering the form deviations, the manufacturing deviations that we were talking about. So the index, the profile, and the lead variations. So these do not affect the actual tooth thickness, but do affect the clearance between those mating parts. Okay, so what we've got here is just a couple of slides showing a few statements that have been asked for clarification, or just to try and clear up some of the remaining confusion. So to start off with, we're looking at the minimum effective clearance. So the minimum effective clearance is the clearance between the actual tooth and the internal and the external teeth of the spline. And that is defined in our case here by the maximum effective tooth thickness and the minimum effective space width. So that will give us our smallest effective clearance. The maximum effective tooth thickness. So this is just looking at how the tolerances all add up. So the maximum effective tooth thickness, that equals the minimum actual tooth thickness plus the total tolerance. So the total tolerance is a combination of these two other parameters that we've been looking at. So the machining variation and the variation allowance. So therefore the minimum actual thickness plus m plus lambda gives us our maximum effective tooth thickness. And in regards to how this actually is input into MASTA, so the tooth thickness tolerances can be specified in MASTA, or the space width tolerances. Okay, so another thing we should note here is that the overball dimensions, which we can specify in MASTA, drive the actual tooth thickness, not the effective tooth thickness. So again, a few more statements to sort of clarify this. If you change the minimum actual tooth thickness down here, the total tolerance will stay the same, and it is the maximum effective tooth thickness that will be modified. So basically, if we modify this, the tolerance will stay the same, and it's the max effective that will be changed. Next, if we change the total tooth thickness tolerance, so the combination of m and lambda, the minimum actual tooth thickness stays the same, and the maximum effective tooth thickness is modified. And then if we change the maximum effective tooth thickness, the minimum actual tooth thickness will stay the same, and is the total tolerances that will change. Okay, so the last thing we're going to talk about here is flexible splines. I've got a couple of slides here to show you, and then we'll jump over into MASTA, where I can actually demonstrate how we would put these in and what kind of results we would see. So within MASTA, we have the ability to replace individual contact splines with FE components, and these are particularly applicable for flexible ring gears. So as with other areas of MASTA, we don't directly replace the actual spline component itself with FE. We are replacing a shaft component with the FE, and then whatever is attached to that shaft can also be replaced. So for example, with the example here, we'll be replacing this actual shaft here, which is the blank essentially. And as part of that model, we're also bringing in the corresponding gear teeth and the spline teeth as well. And that will then be connected into the housing. Now we're going to be bringing in both halves here. So we've got the internal spline half, and we'll be bringing in the external as part of the housing. So in summary of what we're doing here, we're going to be generating condensation nodes on each of the contacting flanks, similar to what you can see here. But we're also able to generate a third node per tooth for the major diameter fit. So as we showed earlier on with the concept spline, with the individual contacts, we can specify a major diameter fit, and that will give us another condensation node on the end of each of those teeth to allow us to constrain it in that location as well. And we should note that spline teeth do not have to be included, but it is recommended that they are included for the most realistic representation of the system. And then in terms of results, that again we'll be seeing in MASTA as we go through the next section. So we've got the deformation of the ring gear can be captured because we have the inclusion of that FE component. So the kind of thing that we can see over on the right hand side there. We can contour the FE component with displacements or stress metrics. Again, as you can see on that image. And this is more representative of the system stiffness for large diameter and flexible splines. And if you're doing some detailed MVH analysis, then it is recommended that this level of detail is included. Obviously, this adds a lot more realism to your model. So if you're doing some kind of sensitive studies such as an MVH analysis, then it's recommended that you do include this level of information. As I say, what we're going to be doing is just converting one of the splines that is in this model from a concept spline that's currently detailed in MASTA to a flexible spline model. So we're going to be focusing on this spline here. So the one that connects the housing to the ring gear. And what we're essentially going to do is replace this spline component here with the two halves of the actual spline component, with the actual spline teeth included in the model we bring in. And then for every one of those spline teeth, there's going to be separate contacts. And it basically means that that spline is going to be flexible, it's going to be able to bend out of shape based on the loads upon it. And obviously it will be much more realistic than the model we have here. So the first thing I want to do here, and there's going to be a bit of jumping around between different modes just to try and get this thing sorted. So the first thing I'm going to do is to actually set this spline to use individual contacts rather than the concept or the detailed spline that we're using at the moment. So if I highlight the spline and go to my editor, now we'll be using this editor quite a bit during this process today. But what I want in here is I'm going to leave it on a concept spline, but for my stiffness type, I'm going to change it from simple. And by simple stiffness, we mean direct specification of axial, radial, tilt stiffness to individual contacts. So the next thing I'm going to do is to actually add the housing component to the model. At the moment, we have no FE components in this model at all. I just want to add the housing. So if I go to my imported FE models, now I'm not going to spend loads of time going through the FE functionality because there's separate workshops and videos available on that. So I'll just sort of skim over some of the functionality for this, just focusing on the splines. So I'm going to make a new FE component called housing. And then I'm just going to, the same as we would with any other housing component, I'm going to import that FE housing. So a full FE housing, import external mesh, and casing with annulus spline. And then just to highlight to you what it is we've brought in reference to the spline. So basically we have the housing, and in this particular model, the spline teeth are manufactured into the housing itself. And what we've brought in here is the housing with the outer spline teeth included. And this is where we're going to be creating some of our contacts. Okay, so what I want to do next is to actually create the condensation nodes. Now, this is the same way as with any other FE model we bring into MASTA. So the easiest way to do it is just to go to the Connections tab and click on the Create Nodes. Just as a brief reminder of what that does, it basically puts a condensation node at various places on the MASTA model where it's expecting connections between the FE component and the MASTA components, and then looks for nodes on the FE model to connect to. So for example, on this bearing, it's created a condensation node at the center there, but it's actually connecting to all of the light blue nodes that you can see there, so at the outer bore, or the outer diameter of that bearing. So what it's done by default for the actual spline is to create a few nodes around that actual spline diameter. At the moment, it's not going to be correct because we haven't set up how many teeth there are, what the spacing is between the teeth, where the teeth are. But we're starting now, so we're getting there with the process. The next thing we need to do is specify whether or not the spline model we're trying to link to has teeth included. So you don't have to include the teeth model if you don't want to, but it does make it more realistic. So we could leave it with X amount of nodes around the outside there and just connect it to a flat surface. That would give us some representation of the spline stiffness and would allow it to deform out of shape. However, it's obviously going to be more realistic if you can include the teeth. And setting up that option is pretty easy. We just go down this list of connections here, which is all the connections in the model. Locate the one which is to do with the spline we're replacing, so annular spline in my case. Ensure we're on a flexible node ring, which is what makes the entire ring of nodes around the circumference there. And then set the has teeth option to true. And what that does to begin with is it makes, instead of one node, it will create two nodes, which is trying to find each side of the spline tooth. So obviously it hasn't done it correctly yet. We haven't set up the search regions correctly, but it's basically looking for create one node on one side of the spline tooth and one node on the other side of the spline tooth as well. Okay, so now we're good to actually go back into our design mode and start modifying some of our spline settings to actually link this up correctly. So if I go back to my design mode, select the spline that I want to modify, and you remember we had all of these settings which we skipped over a little earlier on. The ones I'm going to focus on first of all are these spline teeth settings on the right hand side. So first and foremost, we have the number of contacts per direction. So that is the number of spline teeth. In this case, I know for a fact in this case that it's 24. And it means number of contact per direction. So it's going to make 2 times 24 nodes, one for each side of that tooth. So it's able to contact in both directions if it was taking load in either direction. You do have the option here to custom space the teeth as well. So if you do have an irregular spacing between those teeth, you can manually do it. In this case, it's an equally spaced teeth. Okay, and what you can also do, which we'll modify in a little while, is to modify the angular extent of the external teeth. So how many degrees around the circumference are each of those spline teeth, and what is the angle for the first external tooth. So obviously that's going to change the position of your nodes as well. Before we modify those, I'm actually going to go back to my FE mode. You'll see that even though my nodes are in the correct place, the arrows are going into the teeth, which is not what I want. I want them coming out from the teeth to represent the loading. So this means I need to change the positioning and the span of those teeth. So if I go back to my design mode, if you don't know exactly what these are when you're setting this up, it is unfortunately going to be a bit of trial and error. Hopefully you could be able to figure it out with your own system. I know in this particular case what these values are, so I'm just going to put those in to save us time. My angular extent of external teeth is 7 degrees, and the center angle for the first external tooth should be 11.5. So what you'll see when I enter those in is that the positioning of all the teeth, which is detailed down at the bottom here, are displayed for me. So I can see what the start angle is, the end angle, center angle, and the extent. And if I go back to my FE mode, I should now see that all of my condensation nodes seem to be in the right place, and the arrows, although the pressure angle is incorrect at the moment, the arrows are coming out from the teeth. So I'm happy with how that is set up. Okay, so back to my design mode, and we'll go through a few more of the settings that are available in here. So the first one I can show you here is the type of fit. So by default, this will show you a side fit, which is just where we have two nodes. We have one either side, and we've got nothing constraining it radially here. So there's only the two nodes either side. The other option we have available is a major diameter fit, and I think also coming relatively soon there might be a minor diameter fit, which basically creates a third node for us. So you see here, there's a third node, and basically that's allowing us to actually specify a connection between the major diameter there. So we can constrain it that way as well if our spline asks for such. I'm going to leave it as side fit for this particular case. So the other things we have here are the settings for the individual contacts. So on its most basic form, we have the ability to specify a contact diameter. So this will just control the diameter of those condensation nodes that we've specified. The calculation should be okay in the majority of cases, but you can keep aware of this if you need to change the diameter of that node. And then we have a couple of stiffness values. So we can specify the actual stiffness of the individual contacts. So contact stiffness and tangential stiffness for each of those connections. And we can incorporate a pressure angle as well. So for the pressure angle, it's kind of detailed what the pressure angle is and which way the load is going to go by the arrow here. So if I change that pressure angle to be 0, which is what it is on this particular spline example, you'll see that the direction of my arrow is now perpendicular to the teeth. Okay, and then we also have a normal clearance value as well. So if you've got a clearance between the connections that you want to be able to simulate, so you want to simulate that being taken up, then you can specify a clearance in there as well. Right, and then we do have the spline helix angle options as well. So if you do want to specify a helix angle on your spline, if you do have a helical spline, you can do so. And you can also specify a different helix angle on the left and the right flank of the spline. So just to demonstrate how this is viewed. So what we're trying to do, of course, is select nodes on the FE on the gear tooth flank. So basically we can have a look at the search regions here. Now this is a normal bit of FE functionality. It's not specific to splines. This search region is where each of those condensation nodes is looking for nodes to connect to. So if I've got a helix angle of 0 degrees, it's obviously not going to have any slope to that search region. But if I do modify those, so let me put a slightly different, just to demonstrate. So left flank 15, right flank 20. You'll see there what's happened to the search region. So it's expecting to look in a different place for the nodes to connect to now. In this case, it is 0. Okay, and then the last thing we're going to want to do on the casing component before we perform the reduction is to set up these connections here. So, of course, we want to make sure that we have the correct stiffness specified. In my case, that means these axial clearance bearings. If you're not familiar with these, they're essentially methods of modeling clearances and connection points in your master model. So in this case, there's going to be an axial clearance either side. That's going to give it an axial stiffness because our spline is going to be able to slide otherwise, which is going to be, I think there's a groove which these are going to sit in. So there's one, kind of hard to see. There's one here and one on the other side, which I'm going to try and fit these in. And I can modify these, as with all the search regions, by going to the search region tab. It might be a bit of playing around with the search regions to get this completely correct, but this is the same as it would be in any FE model that you bring into MASTA. So this is going to be a bit of trial and error, so bear with me for a second. Okay, and just to make sure I've not got any overlapping nodes in my case, I'm going to slightly decrease the search region for the actual spline teeth as well. But again, it's circumstantial, so it depends on what your system is. Okay, so I'll go for that in my example. That should be all okay. And then hopefully I should be able to run that one through now. So this will take slightly longer than before, as it's now performing my reduction to all 56 of those condensation nodes, but it is quite a coarse mesh in this example, so it should be fairly quick. Okay, and that is my reduction completed. But remember, all we've done at the moment is one half of the spline. We still need to bring in the FE model for the other half. So I'm going to go back to my FE mode and add in a new model. And this is going to be my ringed gear. And I'm going to import the splined ringed gear. And I'll show you what it is that we're bringing in once it's imported. So there you go. This is obviously a very basic example of what we're bringing in, but it's a complete splined ring gear. So on the outer diameter, we have the spline teeth, which is going to connect to those contacts we've already created. And we have the actual gear teeth included in this particular example as well. So basically, we're going to be replacing this whole section. So we need to make sure that we actually got it set to replace a shaft in the model. So if I go to replace shafts, I need to select the shaft I want to replace. Remember that we can only replace shafts. However, it will replace components that are connected to that shaft as well. So if I select the annulus blank and click on replace, you can see that it brings in all of those components that it knows it's going to have to replace. And then the next thing I need to do is to actually align the models together. Now again, this alignment is something that is not specific to this splines. You would have to do it with any FE model. So I'm just going to say the alignment method is to the replace shaft. And then I know in this case that the alignment axis is x-axis parallel, or anti-parallel rather. You can see those two are now lined up. And then we just need to basically do the same process again. So we need to make sure that we create the condensation nodes. We don't need to go through the whole setup of the node positions and stuff again, as we've already set that up for the spline component when we set up the casing. But I do need to actually tell it that we want to use those nodes. So if I go to my connections tab and create nodes, you'll find that it initially tries to connect them without teeth again. So again, if you've not included the spline teeth in your FE model, you can still use this functionality. It's just going to be slightly less detailed. But if in this case we do have the spline teeth, so we want to make sure that we have this has teeth option specified. Okay. And now what you might notice is that some of the search regions don't line up at the moment. That's not a problem. And obviously it's model dependent. It just means that we need to rotate the ring gear component slightly to make it match up with the other spline teeth that we'd already specified. And I know the value for this. So if I go to my alignment, I think if I put the rotation angle as 8 degrees, you'll see it's rotated that entire component, and the condensation nodes that we've created now line up with those spline teeth. Okay, now again, I'm just going to connect up those axial clearance bearings just to make sure that everything is fine. That one's already got some nodes. So is that one. So I'll just change the length of the search region. And I should be able to hopefully run that one through. So much easier setup on the ring gear model. Because we've already done most of the legwork on the housing, the ring gear is just a few clicks, and that should be all we need. So once this is actually run through, this should be completely set up now. We don't need to specify any components between those connections or anything like that. By specifying it in this way, and using that spline component as a basis, we've actually created the entire contact between the two. So once this is run through, which should only take a couple of minutes, we will go into system deflection mode and just take a look at what we can actually see as a result of this analysis. Okay, so that has successfully run through. So what I want to do now is to actually very quickly just show you the kind of impact this might have on the system. So if I just go to system deflections, it's by far the easiest way to see this. I'm just going to run through one of my load cases. Okay, so we can see already, I've not got any deflection scale on at the moment, but we can see what this is going to potentially do, or hopefully do. So we have our 6 planets in this particular planetary gear set. Those are going to be applying load to the ring gear, and then obviously that's going to somewhat deform out of shape, which is going to have impacts on the system, of course, which we want to take into account. So this is the whole reason for including that flexible spline. So if I start putting this deflection scale further up now, what we should hopefully see is that ring gear starting to deform out of shape based on those loads that have been applied to it. Now, if I refine that down to just the ring gear so we can take a closer look at it, you can see how that is deforming out of shape based on those planetary gear sets. Now, this is the behavior that we wouldn't be able to see if we were just using that simple component. So if we were just using that simple concept spline component, we would just have a node in the middle. So yes, we might see some translation and rotation of the component, but we wouldn't be able to see it deform out of shape. So this is one of the major benefits of using this functionality. And again, we can have a look at the loading on the components. We can contour it, various displacements. And of course, it's going to affect the entire system model as well. So it's not as if it's just an effect showing you what would happen to the spline. That is going to impact the entire system model as well. So if that has any impacts on the misalignment of the gear sets, on the loading on the housing or anything like that, it is of course going to show you that behavior. Take a look at the housing as well. And we can see again the behavior that that is giving us. And just to reiterate, this allows us to specify various clearances in the spline. So if you have clearances that you want to include in there, you want to be able to simulate those clearances being taken up, loading on every individual tooth, this is the perfect functionality for you. So of course the functionality is a little bit more difficult to use than your standard thing in MASTA. But hopefully this demonstration has kind of shown you that it's not too difficult to set up. Especially if you have this video guide as a backdrop, you should be able to do the functionality and perform the addition fairly easily. Okay, so that is about everything for this particular webinar. I hope you found it useful. I'll take a look in a moment to see if there's any more questions come in. Please do feel free to ask away. If I can't answer them right now, I'll be sure they get passed on to the right people and I can send an answer later on. So please do keep an eye out for future webinars or workshops that we will be running. We should be running the next workshop in a couple of weeks' time, which will be optimization tools that are available in MASTA. So things like the design space search, the system optimizer, and the power flow, maybe even parametric study tool, for example. We'll be going through all of those available features. Just to reiterate, the PDF of this session, the PDF of the presentation can be downloaded and you go to webinar window. I will upload the video of this webinar to our Wistia session as well and send out an email to everybody. So all that's left to be said is thank you very much for attending. I hope you found it useful and we'll see you at our future events.